Zimmermann for her last presentation in her mini course. Susanna, please.
Thank you. Okay, all right. So we consider the following homomorphism. So we look at the maps, the group of maps that go AYX plus BY, CYX plus DY, Y. Okay. That's where you send XY onto. And well, A, B, C, and D are rational in Y, and AD minus BC is not zero. So this is a group that is isomorphic to BGL2 of, well, let's say K of Y. So BGL2 of K of Y. And it lives in the group of birational maps of P2 over the field K. Okay, now what we can do, we have a free homomorphism from GL2. That's the determinant. But we mod out by the scalars, so the determinant is not well defined anymore. It's only defined up to squares. Okay, so we look at the determinant. And this ends up in K of Y star, because we're invertible. And then we have to mod out the squares. So here, for instance, we have the element P1 that corresponds to xy, goes to xp of y and then y. And we map it to the class of P. Now here, P, so K of y is a unique factorization domain, so we can decompose P into, like P is a quotient, and upstairs and downstairs we can decompose into prime divisors, into prime factors, sorry. So we write it as, I don't know, F1, E1, Fn, En. And then the Fi's polynomial, they're prime, and the Ei's are integers. Okay. So now we have irreducible elements in one variable. Those give us prime divisors in P1. Okay, so we can map this. To a priori, we want to map this to EI divisor of Fi. Okay. But then we have quotient out by the squares, so this means that our EIs are actually 0 or 1. So here, this ends up in, here we have to give the class in Z2, because we divide it out by the squares. Okay, and what we end up with is, so we send this to the set of the EIs. For each EIs, we have our divisor of Fi, and we end up in the sum of Z2s, where we sum over the prime divisors in P1 over K. And it is not the product, it's the sum, because our sums have only finitely many non-zero coefficients. Okay, these are not infinite sums, these are just finite sums. So we have the direct sum here and not the product. Okay, and so, yes?
One may think that the
Yes, yes. So these are isomorphic. Yeah, this is an isomorphism. Absolutely, yes. So just a different way of noting. You're right. Okay. So what this map does is it counts. So okay, here we have a conic bundle. This is a map of A2 preserving the bundle y equal a constant, y constant. And then the determinant is exactly the fibers that are contracted. Okay. By this map. This is AD minus BC, or P in this case. So what this map does is just counting how many times each fiber is contracted by our map up to parity. So if there's no reason why my P should be reducible, I could have a multiple root, but the multiple root would be sent onto 0. Okay, so I'm just counting the factors up to parity. Okay, and what I constructed yesterday is, what I showed you yesterday is that this homomorphism extends to the Cremona group, not quite this one, after projecting onto the prime divisors of degree at least 9, I can extend this homomorphism to the Cremona group. Yeah, it was yesterday? No, yes, it was yesterday. Time passes quickly, weirdly in this place. So, let's say this is maybe small theta. This is our homomorphism. So FPR from set 2, where I sum over the prime divisors in P1 to, well, the sum, where I sum over the prime divisors in P1 of degree at least 9. Then theta followed by this projection extends to a group homomorphism big theta from yesterday, from BRP2K to this sum here. And extends to a surjective group homomorphism. Well, extends to a group homomorphism, let's say that is non-trivial. Sorry. The surjectivity depends on the field. So maybe I have to add that the algebraic closure of K over K is not 2. If this degree is not 2, it's actually infinite. the Arpin-Shire theorem. And so one of these factors, so this sum, in that case, this sum is non-trivial, and so we have a non-trivial homomorphism. Okay, so this is by, and also should add, this is by Julia Schneider. Or maybe a 19. I'm not sure. Okay, so we constructed this homomorphism by looking at Sarkisian links between Mori fiber spaces, rational Mori fiber spaces, that preserve the conic bundle structure. Actually, the one from P1 cross P1 over the first factor. We could, since we have Sarkisian links and since we have a description of the relations, we can construct other homomorphisms. So what I wanted to do today is just to present two more types of constructions and then say something about higher dimension. No, actually, I want to say something about higher dimension. Okay. So this this construction extends to higher dimensions in the following way. So we have I can actually rewrite what I had before, more or less. So I go from PGL2 to the determinant. Sorry, I'm just writing back down what I deleted foolishly. So, okay, now instead of looking at the maps from before, I look at the following, at the maps, where I have n-1 coordinates, and I send them to a, so this is my y bar, y underscore, ay underscore x, plus b y underscore c y underscore x, plus d y underscore, and then again a, b, c, and d are polynomials in the variables y1 to yn-1, and this time I'm going to work over c just to be sure, and ad minus bc is not 0. So this is PGL2 over c of y underscore. And then I can have the same, exactly same construction, just I replace y by y underscore. And then here, instead of y1, I have p1, I have pn-1. And the rest of the construction is exactly the same. And so this also, after projecting smartly, we can extend this homomorphism to the Cremona group in higher dimension. So this is for any n at least 3. There is a projection PR. There is maybe an index I such that the homomorphism PRI first theta extends to a homomorphism big theta from beer Pn over C to the sum indexed by I. And I is at least as large as C. So initially, I thought I would maybe explain this theorem in higher dimension, but I don't want to go into detail. So I'm just going to give a rough idea. The construction, the idea, the rough idea is really the same. It's really the same as in Julia's theorem. So we have circuits of links. We look at the circuits of links preserving a conic bundle structure, a conic bundle above Pn minus 1, the P1. So we replace P1 cross P1 or P1 by P1 times Pn minus 1 or Pn minus 1. So this is over C. This was over A field K. And we look at circuits of links between Mori fiber spaces so we look at Mori fiber spaces that are as bundles, as Mori fiber spaces birational to this one. So we have Mori fiber spaces X over B, and the commutative diagram like this, and this is a birational map, and this is a birational map. And then we look at circuits of links between Mori fiber spaces like this. And we only keep the circuits of links that, wait, so what do they look like? So P1 bundles. In fact, these circuits of links all look a bit the same. I'm gonna delete this one. So, okay, we have X, B. We take, there is some, a link. What does it look like? There's some, the indeterminate C set is a codimension 2 set. So I'm going to write it in dimension 3. Okay, so this is dimension 2, dimension 3, and then I have a curve. This is gamma. So gamma is the indeterminacy, indeterminacies of phi. This is of codimension 2. And it projects onto a codimension 1 set in B. This is the projection, let me say this is F, and then F of gamma has codimension 1. And then the link is rank 2 vibration above B, so something of rank 2 over B. And it has two birational contractions, one to X and one to X prime over B. These contractions are divisorial. And what it does is it contracts a divisor onto this curve gamma here, and then a divisor onto another curve here. So I have the exceptional divisor of gamma. Then I look at all the fibers containing gamma. This gives me a codimension 1 set. This is a prime divisor. And now on the other side, I can contract the strict transform of this red codimension 1 set. And the exceptional divisor of gamma descends to a surface that is the set of fibers containing the red line. Okay, the red line is gamma prime. And, okay, moreover, gamma prime surjects also to this codimension set. prime, f prime of gamma prime. So this sort of looks exactly like in dimension 2, where I have a P1, where I have a P1 bundle over P1, and I blow up a bunch of points, and then I contract the fibers passing through these points. So they look exactly the same. And so we make, when we construct our homomorphism, we kill all the circuits of links except these ones. Now, this is the basic idea. Now, just like in dimension 2, we saw that we have to kill also the circuits of links of this type that have only rational base points, that blow up rational points. Okay. And the same way, if our curve gamma is rational, we have to throw it out. So what we keep are the ones that blow up a curve gamma that is as far away from rational as possible. And for the surface case, this was having degree 9 or bigger, which was just above the bound we have for the Ribizzo surfaces. Okay? And here we throw every one away. Here we find an invariant that is coming from the boundedness of Fano varieties in the appropriate dimension, and we throw everyone away who doesn't satisfy this bound. So the bound is a covering gonality. Okay, so now replace. So instead of degree of the indeterminacy point, we get something like the covering gonality of gamma. So this is the gonality of gamma. This is, if gamma, sorry, what is this? So if gamma is a curve, this is just the gonality of gamma. Which is the smallest degree of morphisms, of surjective morphisms to P1. And if gamma is of higher dimension, so a surface or bigger, the covering gonality is the smallest integer, at least one, the smallest integer, at least one, such that through every point of my gamma, we have a curve of gonality something. Okay. Curve gon gamma is the minimal integer C, such that there is an open set in gamma, non-empty, such that for every point in gamma, there exists a curve. In U, for every point in this open set, there's a curve in gamma with gonality C. And so now, okay. Okay, so in the for the dimension 2 case, we had a bound with a bound of the Ribizzo surfaces, which is 8 in the sense that so what is that? It's over the algebraic closure, and the Ribizzo surface is a blow-up, is P1 cross P1, or a blow-up of P2 in at most 8 general points. So this is the 8 that we're looking for. Now we want to look for a sort of bound in higher dimension. And what we do is the following. So more fiber spaces, they have So we show that, okay, yes, here we go. Okay, so now in dimension higher, there's a bound on Fano varieties by Descartes. And n is the dimension of these varieties. And we show that if gamma has covering gonality larger than this bound, then the corresponding any relation containing the circuits of links corresponding to gamma is very simple. So they're all like sort of the form. Okay, now I cannot. They're all very, very easy to write down. They sort of look like squares, like in dimension 2. So if the covering gonality of gamma is bigger than dn, then any elementary relation among circuits of links containing the link associated to gamma is very simple. It's more or less, I have, so I've said, I have my x prime over B. And then more or less I have 4 other contractions. And depending on whether they are birational or small, the relation looks a bit different, but more or less, it looks like a square, more or less. Okay. And then, okay, so then the construction of the homomorphism is we throw away all the links except the ones of type 2 that are like this between conic bundles, and whose indeterminacy locus has large enough covering gonality, larger than the bound on Fano varieties. And then the construction of our homomorphism of our map sends these relations to 0. So exactly like in dimension 2, we do exactly like the same as in dimension 2, but we replace the degree of the indeterminacy points, at least 9, by covering gonality large enough. Okay. So this is a very, very vague idea, very hand-wavy idea of it. Okay, so this was the first construction. And I want to go into 2 more constructions. So for the second construction, we want to have, again, we will have a homomorphism from the group of birational maps of P2 over some fields to Z2 sets. But instead of a sum, we will have a free product of Z2 sets. In dimension 2, we will only ever encounter Z2, because a theorem by Stefan Lamy and Julia Schneider says that the Cremona group in dimension 2 over a perfect field is generated by involutions. So we cannot get a Z here. You need to send generators to elements in the group. If the group is generated by involutions, that means the target group is generated by involutions. That's it. So we can never get a Z over 3 somewhere. But then in higher dimension, that's a different story. Okay, so here we concentrate on, so again, we have a homomorphism, no. So we have here worry of P2 over K, which is generated by circuits of links. And the generating relations are elementary relations. But this time, we will not care about circuits of links between conic bundles. We will care about a different type of link, and that's the following. So we consider the following links. We pick a point in P2 over our field of degree 8. So this means we have a Galois orbit of size 8. And we want everyone in the orbit to be in general position. So plus, so to set these 8 points. So then I can blow up this point of degree 8, and since they are in general position, I end up in a de Betzel surface of degree 1. It has, so pick rank 1, pick rank 2. That means its cone of effective curves has dimension 2. And so it has exactly 2 extremal rays. One is the blow up of X, and it has another one. And it turns out that this other extremal contraction is also a blow down, also a blow up, is birational. And it blows down a curve that has 8 geometric components. And so we get down to back to P2. So over the algebraic closure, what we did is we blew up 8 points and we contracted 8 curves, and this gives us a Bertini involution, a Bertini type link in this case. We can see this type of map in a more geometric way. So if we have 8 points in the plane, we have that are in general position. We have a pencil of elliptic curves through it, a pencil of cubics through it. Okay. And if these points happen to be a Galois orbit, great, the pencil is defined over our field. Now the pencil of cubics contains one more base point, which in this case has to be a rational point. Now, we can pick the 9th base point as the 0 on each, on the elliptic curves. Okay. So when we blow up the pencil, this, we get to a surface of degree with k squared equals 0. And it has an elliptic vibration above P1. And the exception divisor of the 9th point is a -1 curve, is a section of the vibration, and we can take it as the 0 on all the fibers. Okay, so and then we do the following. We send Z to YZ on every elliptic curve. Okay, this is an involution. We get back to X, and then since it's again X, we can blow down something and go back to P2. And in fact, this is exactly this map up to an automorphism of P2. Here, blow up X. Sorry. X. So this isomorphism, since this isomorphism preserves the special section that we fixed, it descends to an isomorphism of the de Betzel surface of degree 1 we obtain when we only blow up X instead of X and at the 9th point. And this is called Bertini involution of a de Betzel surface of degree 1, and it descends to a birational map of P2. And now, what are relations containing Bertini involutions? So if we have a rank 3 vibration, and we have our Bertini link. And we have a diagram like this. So our rank 3 vibration factors to both the Mori fiber spaces, through the link. And in the definition of rank 3 vibration, Z has to be, So these are our Mori fiber spaces in the definition of the relations. So B is a point. And in the definition of rank 3 vibrations, Z has to be relatively ample above its base. So Z is at a Betzel surface. So that means we have this was S over there. So S is the Betzel surface of degree 1. We blow up something, we get at the Betzel surface, we cannot blow up anything. So this has to be an isomorphism. And S has pico rank 2. So it has only 2 contractions. So the only links coming from S is the Bertini link. There's no other link. So this means actually a Bertini link doesn't appear in any elementary relation. It's alone. The only relation it has is that it can be an involution. Okay. And so you can move to constructing your homomorphism. So we go to the homomorphism of P2, and we map a link to, so we go to the free product of Z2s, where we we index over the set of Bertini links up to automorphisms of P2. And we map a link to 1 if it is Bertini, and 0 all the other links. And this gives us our desired map. And this construction was generalized by Socrates Sikas to dimension 3. Over C. And this was, I think this was, I think this was in 22. Okay, not sure. Okay, so there's also a homomorphism to a free product of Z2s. Okay, so these are the constructions I wanted to present for BRP2. You can feel free to find your own construction, of course. Again, like I mentioned this yesterday, but like one of the unuseful dreams that I have would be to find like all homomorphisms to Z2. But okay, like I think one needs some determination to do that. Okay, so. What? Okay.
So is there any hope to classify those links that do not appear in any elementary relation?
I think the ones that don't appear in any relation are exactly the Bertini type links in dimension 2. In higher dimension, I have absolutely no idea. There are some examples. It will be in the third construction. But other than those, we don't know. I don't know if there's a general approach that is very promising, but it's definitely something to think about. Okay, so third construction. So the aim is to have a birational map to Z. Okay, and so currently we have this. I mean, when I say to Z, I mean surjective. It shouldn't be the trivial homomorphism. Okay, so we have two constructions, and both. So one is by Blanc, Schneider, and Jasinski from 22, and the other one is by Lin and Ginder, also from 22. It was a bit of a race at the end. And they're both, so I'm going to put C here, they're both for dimension at least 4, and we don't know whether it exists in dimension 3. So the construction that Lin and Ginder did, they have such homomorphisms for fields other than C. And for certain fields, they have one in dimension 3, but not for algebraically closed fields. Okay? I think In dimension 3, they have some for fields of positive characteristic. And the two constructions are very, very different. So the first one, actually this was, okay, was published first and then this one. Okay, so the first one does not use at all the construction I presented this week, completely different one. And then the second one uses the circuits of links and elementary relations among them. While the second one uses more motivic theory and birational geometry. So they're really very opposite. Okay, and I want to present the second one, and then if I have some time, I will say something about the first one. Okay, so the way the construction goes is they start off also in dimension 2, just like the previous constructions. But not on P2. We start on a surface that has no rational points. And we start off on a non-trivial Bauer surface. And what this is just a form of P2 that has no K points. This is a K form of P2 with no points. So no rational points. And they exist. Okay. In fact, any K form of P2 that has a rational point is P2. Okay, so if you want a form of P2 that is not P2, you need no rational points. This is Chatelet's theorem. So if S is a surface that over an algebraically closed field is P2, then S is P2 over our field if and only if S has rational points. Okay. And this is so not just over perfect fields, but over any field. And there are surfaces that don't satisfy this, and they're called the non-trivial Bauer surface. Okay, and the feature of these surfaces is that any closed point in the surface has degree divisible by 3. So if X, so non-trivial Bauer surface, let's call it S. So if S is a point in S, then the degree of this point is some multiple of D. They're fine. This does not depend on the field. Yeah. It comes from the, so there's a classification of Severi Bauer surfaces by a certain type of algebras, and this sort of goes that way. So the automorphism group is a form of a PGL3, and then you go into algebras. Okay, so for links, what does this mean? So you have a surface. If I want to start a link, I have to blow up a point. And I can blow up a point of degree 3, 6, 9, etc. But by definition of circuits of link, here in the top, I have to have a Dilbezzo surface. Okay? Because my Severi Bauer surface has actually pick rank 1. Okay. So this means, okay, so if this is the start of my link, so this means that the degree of my point can be 3 or 6. If it is of degree 3, then I blow up an orbit of size 3, and I have an orbit of lines, of 3 lines passing through 2 of the points. When I blow up, I will get a form of a beta surface of degree 6. Okay, I have my red points. I have 6 minus 1 curves. 3 of them are coming from the exceptional divisors of the points, and then I can contract the other 3 onto a point. So if I start with S, Serre-Brouwer surface here, in general, I will arrive here at something that is called the opposite Serre-Brouwer surface, and it's not necessarily isomorphic to this Serre-Brouwer surface. So actually here, so this is a version of the standard Cremona map. The standard Cremona map goes from P2 to P2, but here in this version, I might leave my BRS. I go somewhere else. And then, so this is the degree 3. And then degree 6 is I have 6 points and an orbit of 6 points. That is still, these points are permuted somehow. And through 5 points, I have exactly 1 conic. So this gives me 6 conics that are permuted somehow. Okay. And what this link does is I blow up the 6 points, and then I contract the orbit of the 6 conics passing through the 6 points. So I start on S, and then I arrive on S or S up. So these are the only 2 types of links that I have starting from this surface. And what they show, what Blanche, Schneider, and Jasinski show is that these links, they don't appear in any elementary relation. And the reason is, again, if I have some rank 3 vibration, that dominates this link, then since S and S up have pick a rank 1, B is a point, okay? And then S prime prime is a Delpizza surface. So I start on S, I blow up a point of degree 6, and then I only have I can blow up points of degree 3, 6, 9, blah, blah, blah. Whatever I do, I will certainly not get any more Delpizza surface. So this has to be an isomorphism. So these don't appear in elementary relations. These type of Cremona maps, they appear in elementary relations. And what they do with it is they construct a map from Biomori S to first a sum of Z3s, and then a free product with a big free product of Zs. And they send the Cremona, quadratic Cremona type maps to Z3s. And these type of links to Zs. Okay, so let's say the one with base points of degree 3, they go here, and the one with a base point of degree 6, they go to a 1 here. And with a bit more work, they show that this is really, that all elementary relations are mapped onto 0. So we can, over non-rational surfaces, we can get a Z3 or a Z. Okay, so the reason why they looked at this is because they wanted to look at Mori fiber spaces whose generic fiber is a form of P2. Okay? So now we go to dimension at least 3, and we look at a Mori fiber space such that the dimension of X minus dimension of B is 2. So then the generic fiber is a surface. Okay, and so we want that the xk of B over the algebraic closure is a P2. So if we want this, we have to ask that the generic fiber has no rational points. And this is only possible if the dimension of X is at least 4. Because otherwise, I think K of B is a C1 field, and then you can apply Zen's theorem, and you find a section, and a section is a K point in the generic fiber. Okay, this is nice theorem. Okay, and then so question pip. Okay, and then, so let me write down the generic fiber. This is now a non-trivial silver Bauer surface. And we can have links of the generic fiber. So we have maybe a point of degree 6. Or 3. A point in a generic fiber corresponds usually to a section. I need to correct this from Tuesday. So point, so a point, I will change my point. A point in the generic fiber corresponds to a n-to-1 section, maybe not n-t, where t is the degree of the point. In the sense that if you have your generic fiber, and you have a rational point, this corresponds to a section. If you have a point of degree 2, this is a Galois orbit. This corresponds to maybe 2 sections, but they're exchanged. The point is exchanged by the Galois group, and so what you get is a double section. 2 to 1. It could be 2 disjoint, you get a double section, an irreducible one. So now we have a point of degree 3 or 6, and we can do a Sarkisov link starting with that point. We go to Let's say this is now S. We go to S, the opposite S. And this induces us a birational map from our vibration, from our Mori fiber space, to another variety with a contractional fiber type over B. And in the sense that this is a birational map, and if you restrict the birational map to the generic fibers, it gives you exactly that link. And then a priori, you could have done something wrong. Maybe this is not a Mori fiber space, but you can contract a little bit and get a Mori fiber space. So you can assume that this is a Mori fiber space. Okay. And so what Blanc-Schneider and Jasinski do is they find examples, explicit examples, and of these Mori fiber spaces, and they compute that their generic fibers have points of degree 6 that are in good position. So there are these links between the generic fibers, and therefore they get these birational maps between Mori fiber spaces. And then they compute all elementary relations between Mori fiber spaces that are equivalent to this one, containing a link of this type. And with this, they construct a birational morphism from the group of birational maps of X to a sum of sets. Okay. That is surjective. And they do this, so they show that they can do this construction for this type of Mori fiber spaces where X is rational. Okay, so for rational. So all this is over C. And I think their indexing set is as large as C. I would have to check. So this gives you an idea of how large Cremona groups in higher dimensions are, because almost any group we can think of is a quotient of a Cremona group. So they're huge. Yes, yes, exactly. Yeah. Absolutely, yes. And the construction fails in dimension 3 because we don't have any Mori fiber spaces of dimension 3 that have a generic fiber and non-trivial Serre-Brouwer surface, because the generic fiber will be over the field K of T, and that means there's a, by its N theorem, this means there's a section. So this one has a rational point, so completely fails. And I think for the moment, at least, I don't know anybody who has outed themselves as having an idea of what to do in dimension 3. Maybe they have one, they're keeping it secret, who knows, but I don't know. I don't actually know. I think we, I don't know. Yeah, I don't know. I keep going back and forth between yes, there is one, yes, no, there is no. Okay, I wanted to say something about the other homomorphism construction from BRPN to Z, the first one. is also for dimension at least 4. And the idea is actually really cool. So we take, so what do we do? Who is DC? So we take a map. Actually, it's not set here, it's somebody else. Well, let me go. So I take a map from Pn to itself. And I look at what is the indeterminacy locus of that map. And I look at the parts that are of codimension 1, the divisorial part. And I say C of F. So this is the sum of classes E, where E is in the indeterminacy point of F of codimension dimension n minus 1. And I do minus the sum of certain divisors in the indeterminacy of the divisors in the indeterminacy points of the inverse. And the classes I take are the classes in the Grothendieck ring. Where you can add, so what was it? So if I have a variety and I take away a closed subset, I do x minus z is y. Okay, and then you have a multiplication, and that's coming from products. Okay. I'm sorry?
You mean the divisors that are contracted?
Yes, yes, thank you. Yes, divisor, yeah. Oh, yeah. Okay, divisors. So let's say prime divisor contract. Yeah, you're right. The indeterminacy set is codimension 2. I cannot. So this is a hypersurface contracted by F inverse. Thank you. That's for the, yeah. Okay, and this is in the group. So of varieties of dimension n minus 1 up to some equivalent. So the Groton ring a priori, and then you can go further. And so they show that this actually defines you a homomorphism from the Cremona group to this group. Okay. And they show that this is non-trivial. And for this, what they use is an example of a birational map described by Lai and Hassett. Which is a birational map of P4. And it has its indeterminacy locus is a K3 surface. And the indeterminacy locus of the inverse map is also a K3 surface, but they are not equivalent in the Grothendieck ring. So this is maybe phi. So there is a hypersurface contracted onto that K3 surface, and there's a hypersurface in here contracted onto that K3 surface. And they show that this particular map, in the case of n equal to 4, has a non-trivial image here. Basically, that this has non-trivial image there is part of the result of Lyon-Hesse. So they take this example and they get immediately that the image of this map is non-trivial. And then for higher dimension, what they do is just cross P1, cross Pn minus something, and they get the analogous result. And so the smallest example that they have is in dimension 4. So also a priori, so it's not that their construction fails in dimension 3. In dimension 3, we just don't know whether there's any element in the Cremona group that gets mapped to a non-trivial element. We don't know. We don't have an example. But over certain non-closed fields, there are examples. And so if I'm correct, over some finite fields, or at least fields of positive characteristics, there are these examples with 3 here, and then some curves, some interesting curves here. Okay. And yeah, that's all I wanted to tell you.